Okay, so today we're going to be looking at reversible reactions. Now, our syllabus outcome is to model static and dynamic equilibrium and analyze the differences between open and closed systems. So, some revision from last lesson. Make sure you've had a go at answering the questions first, but I'm going to go through the answers now. So, reversibility largely depends on the thermodynamics of the reaction, so things like delta H, delta G, delta S, temperature. If reaction's exothermic and increases in entropy, then the forward reaction is spontaneous while the reverse reaction is not. If the reaction is endothermic and there's a decrease in entropy, then the forward reaction is non-spontaneous, so always non-spontaneous, while the reverse reaction is spontaneous. And if enthalpy and entropy have the same sign, then it will be reversible depending on the temperature. So let's have a look at today's stuff. So reversible reactions. Now, in a one-way reaction, when reactants are placed into a reaction vessel and allowed to react, products are formed. However, what happens during a reversible reaction where the products themselves can react? Well, what happens is in the reversible reactions, when the reaction is stopped, some of the products will have formed, but there'll also be some reactants left. So we get this mixture of products and reactants. And this is what we call an equilibrium state. So it's not um, it's equalized, okay? So there's no current reactions going on. It's sat there, that concentration is maintained. So that's our equilibrium state. It's at equilibrium. And this is what I mean by that. So this is an example here. We've got a reversible reaction where we start off with reactants. Slowly over time, the reactants are used up. The concentration goes down, goes down. So it goes down, slows off, reaches a point where it becomes constant. Okay. As the reactants react, products are formed. So we get the products coming up here. And the same thing, as the reactants slow down, so do the products, and it reaches this constant state again. And this is the point where it reaches equilibrium. So from here on out, that's the point where it reaches equilibrium, where the concentration stays the same. Okay, so that's as far as that reaction goes. It's at equilibrium. No more reactants become products. It just stays at that concentration. Now, that's what we call a static equilibrium, where it kind of just stops. However, what actually happens, the products also react to form reactants. So we get the reverse reaction happening. At the same time, reactants will react to form products. So we actually get both reactions happening at the same time. It's a backwards forward, so reactants become products, products become reactants in this great big cycle. And we call that a dynamic equilibrium. Okay, so much like in physics, how we have static and dynamic, static meaning not moving, dynamic meaning moving, a dynamic equilibrium has the reactions constantly occurring, constantly going, but the concentration stays the same. So we've still got that equilibrium state, but it's constantly reacting. Now, how does that happen? Well, basically, we get to a point where the rate of the forward reaction is equal to the rate of the reverse reaction. So however many moles of products are formed is the same number of moles of reactants that are formed. Okay, so it just goes backwards and forwards, but the concentration doesn't change. And that's one of the key things. It means that while it's continuously happening, the overall concentration of the reagents remains the same. So here's an example. So we've got reaction rate versus time in our first graph. We can see that we've just put in reactants. There's no products at the start. So we have the forward reaction starts to occur, and it produces some products. Those products then react and start to form reactants. But because of the mismatching concentrations, we get a large amount of the forward reaction happening, very little of the reverse. As time goes on, less of the forward reaction occurs because there's less molecules there. More of the reverse reaction occurs because more are there until we reach a point where the reaction rates are equal. Okay, once the reaction rates are equal, equilibrium is reached. Now that's this point here. Okay, now I know it looks like the red and blue are kind of above and below each other, but they're meant to be at the same point. Okay. Now, even though the reaction rates are equal, it doesn't mean that the concentrations are equal because there's all sorts of thermodynamic and collision theory things involved, which we'll actually do next lesson. Um, but what we get, so in the second graph, we have concentration versus time. We can see that the reactants, most of the reactants are used up and we get mostly products. But we still have that thing. Once it reaches equilibrium, we have constant concentrations. So they don't have to be equal, they have to be constant. But the reaction rates have to be equal. Now, requirements for a dynamic equilibrium. So there's two main requirements. The first is that the chemical system involves a reversible reaction and it is a closed system. So what we mean by closed system is that, sorry, there's more on that soon. So we'll get to that shortly, but it needs to have a reversible reaction and a closed system. Now, what that produces, it produces a dynamic equilibrium um, system that has these three properties. So the rates of the forward and reverse reactions are equal. The concentration of the reactants and products remains constant. And the macroscopic properties are also constant. So when I say the macroscopic properties, we're talking usually about physical properties. So things like color, that sort of thing, state. If we've got anything changing, then it's not an equilibrium system. Okay. The example I like to use is some of the clock reactions that go, between colors. Um, that's not an equilibrium system. Like we do have reversible reactions. We have it going one way and then the other, but it's not a equilibrium system because they're not happening at the same time. Okay, they're not occurring at the same time. It's not. Um, there's no constant macroscopic properties. Okay, if it was a case where some of the molecules are black and some of them are white, and then they switch, as long as the overall macroscopic properties are constant, then it could be considered an equilibrium system and a dynamic equilibrium. But if the macroscopic properties aren't constant, it's not a dynamic equilibrium. Now, also going to have a look at chemical systems. So there's three main types of chemical systems: open, closed, and isolated. So an open system, that's a chemical system in which both matter and energy are being exchanged with the surroundings. So we can have a look at this example of um, a pan boiling some water. Now, as we boil water on a pan, we're putting energy into it in the form of, however we're heating it. Energy can go out as well, so it can be cooled. Some of that energy can be lost. But most importantly, the matter can come out. So as we're boiling water, the water evaporates and leaves. Now, as it does that, it exchanges with the surroundings. So that water will eventually be lost. Now, a closed system. So a closed system is a system in which only energy can be exchanged with the surroundings. And this is the one that is required for an equilibrium system. Now, in a closed system, we can get exchange of energy between the surroundings and the system, but matter cannot be exchanged. Okay? Basically, in this case, imagine a pressure cooker. So in a pressure cooker, you've got the lid on, it holds all the water and everything in there, but we can heat it up. So we can put energy in and we can take energy out of the system, but the matter that's in there stays in there. The other type is an isolated system. Now, this is probably the best analogy we can give you for an isolated system, which is just a thermos in which no matter is exchanged, no energy is exchanged. So it's isolated from the rest of the universe. Now, obviously, a thermos will eventually warm up. There is some exchange of energy, so it's not the greatest analogy, but it's probably the only one that we can realistically use because there's very rare, it's very rare for something to be isolated. I think the only real isolated system is the universe as a whole. Okay, if you average everything across the universe, it's isolated. There's nothing that no energy can go in or out. It's just it, or no matter can go in or out of the universe. It's all left in here. Okay, for summary, dynamic equilibrium is where the rate of forward reaction is equal to the rate of reverse reaction. Probably the most important part. At equilibrium, the concentrations do not change. Okay, and the dynamic equilibrium requires a reversible reaction and a closed chemical system. Now, the activity for this is modeling dynamic equilibrium. Basically, we can use some dice to model the forward and reverse reactions. We get 100 dice, we roll them. Let's say every 4 that we roll is classed as a successful collision. Those that get then transferred to the product side, they're now products. So we roll the reactants again, pick out any 4s, but before we transfer them across, we also have to roll the products because the products are also going to react. And any 4 that we get on the product side becomes a reactant again. Okay, so there's this constant roll, swap, roll, swap. And if we make sure we count the amount of dice that are exchanged and the dice that there are, we'll actually see a graph similar to that one earlier where we saw the reaction rates changing and becoming equal, and then the actual amount changing and then becoming constant. So the amount of dice should remain constant because that's our concentration effectively. Okay. And so that's it for today. Thank you.